Okay, the homework from yesterday. You guys wanted me to start with 6, I think I heard from you.
6 and 7.
Okay. So this has 8 and fluorine has 7, but I've got 4 of them, so that is 28 for a total of 36. Okay? So xenon's going to go in the middle. And I've got fluorines coming out of the xenon, because remember, fluorines always have to be on the end. They can only bond with one other thing. Okay. Xenon, because it's in a period 3 or higher, can expand its octet and make bonds into that D level. Remember we talked about that yesterday? How we can expand into the D level and use that for bonding. So at this point, I have 8 electrons placed, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36.
Yeah, that is weird.
All right. Phosphorus then, 5, and then 7 times 5 is 35 plus the 5 gives us 40 electrons in play. Again, phosphorus is period 3 or higher, so it can expand its octet, so it can take in all of these chlorines. So we're going to have the 5 chlorines coming off of here. At this point, I have 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40.
How do you know if you can put the lone pair on the xenon one?
On the xenon here, because xenon is period 3 or above, and that means that I can expand the octet of the central atom.
So like if it even if it didn't have right. So like if those didn't have the chlorines, could you on the bottom? Could you still put the dots on the phosphorus?
Yep.
Okay.
So if this was like PCl4 instead, I'd have fewer electrons, but yeah, I would have to put some stuff on lone pairs on the phosphorus then. All right. What else? Anything else? Do you need me to do 8?
Sure.
Yes, absolutely.
Okay.
Do any of them actually.
All right. So 8, they've partially drawn it, so we have to figure out what we're missing here. Okay. So all of our carbons, we have 4 carbons placed, so we don't need to place any more carbons here. I'm going to get 16 electrons from those carbons. My hydrogens, got the crud. I've got 7 hydrogens here out of 8. So I'm going to end up with 8 electrons after hydrogen, and I need to complete this drawing with another hydrogen. My oxygens, neither one of them are on there, so I'm going to have to place 2 oxygens on here as well. Okay, so the oxygens are going to bring 12 electrons to the party for a total of 36. Now, if I draw this, I'm going to draw it wrong, just so you know. So if you want to like hold off on drawing it in. If I do this and I put my oxygens here and my hydrogen here, okay, and I go and I try to use up all 36 of these electrons. So right now I've got 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. I'm out of electrons. And this guy doesn't have a completed octet. So I can't do this. Okay? So I'm going to have to go in. I'm going to take this hydrogen here and I'm going to attach it to this oxygen. And at this point now, I have all 36 electrons placed. Don't draw it yet. It's still not right. Why? Do you see this carbon here? That carbon only has 6 electrons around it. It needs 8. So what I'm going to do is I'm going to pull these 2 electrons out, and I'm going to do a double bond right here. That doesn't look good. Let me try that again. I'm going to do a double bond here between that oxygen and the carbon. And that's going to give me my full octet and give me all 36, sir. Not with the hydrogen attached to it. Could I? Okay, let me try something. Let me just see if I could do that. Hold on. So if I had this, and you want me to do that. 2, 4, 6, 8. So that's 2, 4, 6, 8. Okay, so 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So yeah, I guess this would work. We're going to learn today why this isn't the best structure. Okay. Right now, with what you know about Lewis structures, this would be acceptable. After today, this isn't going to be acceptable anymore. Okay. And I'm going to show you why here in a couple minutes. In fact, I'm going to take a snip of that because we want to come back and we want to talk. Hopefully we'll have time. I can talk to you about why that's not a good structure. Okay. And why the first one that I drew was. Okay. But with what you know right now, that would be fully acceptable. But that's what leads into our discussion today.
You don't want what?
To look the other way.
Like Medusa, if you look at her, you do the stone.
Yeah, sure.
I'm sorry.
I'm so sorry.
My big old feet.
Make all.
Is that like the second day of
Make all. What size do you wear?
Girl, if you don't turn around.
Not you clocked your teeth. Not you clocked your teeth.
You're sassy little spider monkey.
Let's see. What do I even mean?
I'd like it.
Oh,
I have
wow.
these kind of
What that?
You already finished it?
Why?
No, I don't know. But I mean, I did. I'm really hungry.
Why do they have claws?
All right. So that leads us into our discussion here of something called resonance and formal charge. All right. So resonance is where you can draw a Lewis structure and you can find more than one arrangement where the electrons are equally valid. And it typically is where you're going to have a double or a triple bond where you can place that in more than one spot. So for example, if we look here at nitrite ion, this double bond with the oxygen could be on this oxygen or it could be on this oxygen. Okay, so that it could be drawn either of these two ways. Does that make sense?
Okay.
And either one of these would be a valid structure. Now, in reality, what is happening with this resonance is it's not really a double bond here and a single bond here. It's kind of a mashup between the two. Okay. So when we look at that, we go into something called bond order. Okay. The bond order of a double bond is 2 and the bond order of a single bond is 1. But the way we calculate bond order is number of bonds. So how many bonds do I have here? 1, 2, 3. How many bond sites? 1, 2. We divide that out and we get 1.5. So instead of this being a double bond and a single bond, it's actually more like a 1.5 bond and a 1.5 bond. It's like a mashup. Okay. And if they ask you to draw all resonance structures, you'd have to draw both of these. And that happens sometimes. Okay. Now, what is bond order indicative of? Is that a big word? Do you know indicative of? You know what that means? It indicates, yeah. Okay. So what bond order equates to or indicates to, it's indicative of, is the strength of the bond. The higher the bond order, the stronger the bond. So if you had something that is double bonded, it's going to be stronger than something that's single bonded. It also tells you something about bond length. A double bond is shorter than a single bond because it's kind of like two things holding it together. So it kind of like pulls it together tighter. Does that make sense? So a higher bond order means a shorter bond. All right. And that's what I've talked to you about in that previous drawing is what's on these two slides here. Okay. Here's an example. This is ozone. Okay. So this is what ozone looks like. So the bond order here would be how much? How many bonds do I have? 3. How many bond sites? 2. So its bond order is 1.5.
Just kidding.
1, 2, 3 bonds.
No, I thought it was the whole thing. I was just.
Okay. Yeah. This thing down here is the same as this. It's just showing the double bond on this side here and the double bond on this side here. And either one of these drawings would be valid. You know, valid, yes? Okay. So this bond really isn't a double bond. It's more like a 1.5 bond. And this bond isn't really a single bond. It's more like a 1.5 bond. Because it's kind of a mashup between the two. It's saying like, you know, it's kind of a mashup between these two options here. This is kind of a mashup between these two options. And that's what resonance is. If you go on and take AP Chem with me, we talk about resonance a lot. A lot. But it's not that hard a concept, right? You guys are okay with it? All right. So that is resonance. The other thing that can change in terms of our drawings is something called formal charge. And that's where this drawing that we had drawn, that we were just talking about, that's why this drawing is going to be wrong. And I'm going to show you why that is coming up here. Okay? It all comes down to this idea of formal charge. Now, there are a lot of different ways to calculate formal charge. Many of them will make you cry. They're very complicated and icky. Okay. When I was first teaching this to AP, I was in tears over this. Okay. Because I could not figure it out until I stumbled upon this method, should minus has. This is easy. Okay. I promise you, just stick with me. Okay. Don't give up on me. And you can do this. It's not bad at all. No.
Are you gaslighting me right now?
No, I'm not. No, this is not going to be bad. Trust me. Okay. Just watch. All right. Once I fell into and found this method, I was like, oh man, That's so easy. Why do these other people make it so complicated? Because they can, but they don't need to, because this is easy. Okay? So this is should minus has. When multiple structures are possible, you're going to use formal charge to determine which one is best. You are going to calculate formal charge with the should minus has formula. Should is the number of valence electrons an atom should have. You're just counting how many valence electrons it has off the chart. Hydrogen 1, next column 2, skip a few, 3, 4, 5, 6, 7, 8. You guys have been doing that. You can find should. Everybody should be able to find should. Okay? Yes? You remember how to find should? Okay. All right. So should is easy. Had isn't that much harder. Or has. Sorry. Got my tenses wrong. Okay. Has is the number of electrons directly attached to the atom. I'm going to show you. Just hold on. Breathe. It's not bad. I'm telling you, it's not bad. The best structure is the one with the formal charge as low as possible. You're hoping for 0. If you have to have a formal charge on something, the negative formal charge has to be on the most electronegative atom. And this is the only time that we do this. When counting the has, a bond only counts as 1 electron. But that's the only time. It's the only when you're doing this calculation. Well, watch how it goes, though. It's going to be easy. Just chill out. Flip to this one. Bear with me. This is not bad. Watch what I'm going to do here. Okay? You're going to be okay.
It's smaller than mine.
What?
It's tiny.
Is it bigger here? Get it bigger?
No,
On
on
the
our
board,
paper.
it's big on the.
On our paper, it's really small.
Well, you've got extra room at the bottom, don't you?
Yeah, I was just like,
Or at the top above there?
yeah, I was just like saying out
Just
loud.
expand.
Yeah, right.
All right. So we are going to figure out our should values here for these.
Oh, good job.
So we're going to look on our periodic table and we're going to find nitrogen and you're going to tell me what column it is. 1, 2, 3, 4, 5. You're good? Okay. So that's our should. See, that's not bad. You can do that.
I'm okay.
Now, this is the one that's a little, just an itsy bit harder, but not much. Okay? Watch. You're not watching. You're looking in the back. You're not watching. Put your eyes on the board.
Okay.
All right. Here I'm going to start counting. 1, 2, 3, 4, 5, 6. And the only time we count this as 1 is when we're doing formal charge. This is 7. So our has number for nitrogen is 7. 5 minus 7 is, no, not 2, minus 2. Good. All right. Now let's count carbon. How many should carbon have? 4. We're going to count how many it has. 1, 2, 3, 4. 4 minus 4 is 0. How many should sulfur have? 6. How many does sulfur have? 1, 2, 3, 4, 5. You got it? You're seeing it?
Oh, I'm seeing it all.
Is it making sense?
Oh, it's making sense. All right.
Okay, so 6 minus 5 is 1. Now, if we want the overall bond order for the whole molecule, we add these together. What does this add up to be? -1. it should match up to whatever charge you have up here. So if it's not an ion, all of these should end up adding up to 0. All right, let's try another one. Are you able to see that the should values are going to be the same here? Because they come right off the periodic table. Okay, so nitrogen should be 5 because it's in the 5th column. Carbon should be 4. Sulfur should be 6. Now we're going to figure out our has value. How many does nitrogen have here? 6. 1, 2, 3, 4, 5, 6. So 5 minus 6 is a -1. Carbon has how many? 1, 2, 3, 4. Sulfur has 6. 1, 2, 3, 4, 5, 6. If we add all these up together, they come out to be -1, which again matches up. All right. 5, 4, 6. See if you can figure out what the has is for these 3. Need more time? All right. For nitrogen, you should have gotten how many? 5. 1, 2, 3, 4, 5. For carbon, you should have gotten 4. 1, 2, 3, 4. And for sulfur, you should have gotten 7. 1, 2, 3, 4, 5, 6, 7. So that's a -1. All right. Now, if we look at this, the way it's drawn here, we have to figure out which one of these is preferred. So if we go back to those rules, one of the things that I said was you want to try to have a formal charge on as few things as possible. So based on that, what you know with that rule, which one of these are we going to get rid of right away? The first one. The first one has a formal charge on 2 different things. So we're going to get rid of that guy. He's no good. Now we have to figure out which one of these 2 we want to go with. Well, we said that if you have the ability to, you want to make sure that your negative formal charge, so negative formal charge, is on the most electronegative element. So which one of these, sulfur or nitrogen, is more electronegative? Nitrogen. It is a 3. Sulfur is a 2.5. So which structure is more electronegative and the negative charge is on? Which one do I want to go with? This one right here. Because the negative formal charge is on the more electronegative element. The negative formal charge is on the more electronegative element. Now, let's look at this guy that we did from the homework, okay? When we drew this like this, when we had this drawn, we were at the 36 electrons that we needed. Here, my carbon should have 4, and it has 4, so it's at 0. This oxygen should have
6.
6, and it has
8.
1, 2, 3, 4, 5, 6, 7. So it's at a negative 1. This oxygen should have 6, and it has 1, 2, 3, 4, 5. So it's at a positive 1. Even though my whole structure is at 0, I could build this better and end up with a 0 formal charge. So if I were to take this and have this guy over here and have this guy right here, now let's check and see. Well, now this guy is at what for its has? It's at 0 for the formal charge. Its has is 6. So it is at 0. And this oxygen is now at what? 6. So it is at 0. So this is why your building of your molecules comes down to formal charge. Okay? Because like I said, even though, as of before class today, that other one was valid, now it's not, because it's going to come down to formal charge. Because we could build this in such a way that nothing has a formal charge on it. And that's the accepted form. Yay? All right. Let's try a couple more here. Here is this one. See if you can figure out the formal charges on these and which structure is the best. All right, were you able to figure out which one's best? First one or second one? First one. There's 0 formal charge on any of this. This one we have formal charges, and there's another problem with this. What's the other problem?
The oxygen doesn't have enough.
Well, the oxygen has the positive formal charge and the carbon has the negative. Remember, your electronegativity increases as you move across. So oxygen is more electronegative than carbon. This needs, if you had to have a formal charge on stuff, the oxygen is the one that should have the negative formal charge, not the carbon. So this one's a bad structure for a couple different reasons. All right, nitrate. So nitrate, the formula for nitrate is NO3 with a -1 charge. See if you can figure out the structure of that guy. All right. How'd you do on this guy? Did you get the same thing I got?
Yeah. No.
Okay. Can you share with me what you got that was different, please?
No thanks.
No, come on. Somebody. I want something to work off of. Somebody share with me. Yes.
Well, at first I had everything without double bonds. I just had all
Single bonds like this. Okay.
That's what I have.
and then fully filled out.
Okay. So right now I have 6 out of 24, right? 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What's the problem? I ran out of electrons. What's wrong with my drawing right now? You see an issue here? You know, the nitrogen doesn't have an octet. So I can't keep it like that. Nitrogen has to have an octet. I don't have any more electrons to put lone pairs on that nitrogen. So what do I got to do? I got to pull it into the middle, don't I? Okay. So I'm going to pull that in. And now, you know, I've got to have it in brackets like this. Did it matter which one of these I pulled in? Could I have pulled this one in and brought it like that? Yes. What are these called? These forms are called, what did we talk about at the beginning? Yeah, resonance. Okay. So these are called resonance structures. Is there another way for me to draw this? Yeah, there's a third way, which involves that double bond being on the bottom here. All right. If we look at formal charge, what is the formal charge on this oxygen right here? Should. How many should oxygen have?
6,
It has how many?
7.
7. So it's a -1. This oxygen is a,
Same.
it's the same thing. Yeah. If you can recognize this structure is the same as this one, it's a -1. What is this oxygen? 6 minus 6, which is 0. And what about my nitrogen? How many should nitrogen have? 5. How many does it have?
4.
So it is a 1. Now, if I take this 1 here and add it with this -1, this -1, and the 0, what is my overall charge on that item? -1. That's where we're getting that -1 from. And these are called resonance structures. What is my actual bond order here for this? How many bonds do I have? 1, 2, 3, 4 bonds. How many bond sites? 3. 4 divided by 3 is 1.3. That's the inverse. Okay, so 1.3. So these are going to be stronger bonds than if they were all single. And in reality, these are all like, 1.3 bonds instead of one or a single bond or a double bond. All right, nitrate makes sense? All right, hydroxide's pretty easy. We're going to skip that one because we're running out of time. Let me make sure. Let's skip down to the we-dos here. Or the we-dos, you don't have a video on this, do you?
Did you say?
Nothing. Don't worry about it.
Is this packet gonna be homework?
Yeah. Do you want me to stop now and give you time to work on homework, or do you want me to keep going with examples?
Just go through.
Okay. All right. I'm not going to make it the homework due, though, until Friday.
Be right back.
Because tonight I want you concentrating on trying to get ready for that vocab quiz. If you don't have time for this, then you're going to hold it off and work on it tomorrow. Okay? Okay. So you'll have to make it up when you get back, okay? Or what are you doing tomorrow? A field trip? Okay, that's fine. If it's not a field trip. If it's a field trip, I want you coming in before school, before the field trip. But if it's something else, don't worry about it. All right. So we're going to count up how many electrons we have at play here. This is 6 for sulfur, 24 for oxygen, and another 2 here for our -2 charge. So that's a total of 32. Is that right? Yeah, 32. Yeah, that makes sense. Okay. So I'm going to start by putting my sulfur in the middle, and I'm going to put my oxygens around it. And then I'm going to start filling in and trying to use up all 32. Right now I've got 8 in place. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And then what else do I need to do to this? Well, sulfur has a full octet right now. Yeah, everything has an octet.
The bracket.
Yep, I need a bracket around it. Now, let's check our formal charge on this. Because I think there might be a better way of drawing this. Check my... Yeah, that's what I thought. Okay. So, check our formal charges here. Formal charge, all of these oxygens right now are the same, aren't they?
Yeah, 7 and 6.
Yep. So it should have 6. They all have 7, so they're at a -1 charge. Sulfur should have 6. It has 4, so it is at a +2 charge. Is there a way that we can build this, that we can minimize this charge? If I do that, am I still at 32 electrons? There's 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now, what have I done with these 2 oxygens as far as their formal charge? These double bonded oxygens are now 6 minus 6. So they're coming in at 0. What's happened to my sulfur here?
6 out of 4.
Count again. 1, 2, 3, 4, 5, 6. That's also at 0. So I've got this times 2, which gives me my -2, which syncs up with that. And I've got everything else at 0. Now, why can sulfur have 6 or 12 bonds, 12 electrons, 6 bonds around it? Yeah. Yeah. Yep. It can expand into that D level. Okay. So because of that, we're able to do this. Now, does this have a resonance structure available to it? Yeah. Could I draw this with the double bonds here and here? Yeah. Could I draw it with a double bond here and double bond here and single? Yeah. Okay. I could draw all of those other permutations if I needed to. All right. So So, any questions about that guy? You've got 2 minutes. Do you want me to do another one or do you want to pack up?
Pack up.
Okay.